What are hydrogels made of? Come and join us explore the building blocks of tomorrow's materials. Hydrogels are fascinating materials. They form three-dimensional networks capable of absorbing and retaining a lot of water. Imagine a sponge that can hold over 90% of water. These gels are made by linking hydrophilic polymers, giving them a flexible, tissue-like feel. The swelling of hydrogels depends on several factors. First, the composition of the polymers affects how much water it can absorb. Second, the density of cross-linking makes the network more rigid and less absorbent. Third, environmental conditions like pH, temperature, and ionic strength play a big role. And lastly, some hydrogels even respond to the external stimuli like temperature, pH, light, or electric fields. Hydrogels have some unique characteristics. They have high water content and are very absorbent. Their structures are held together by various forces like covalent crosslinks, ionic forces, hydrogen bonds, and more. These materials are highly flexible and have excellent transport properties, are biocompatible and can even be injected. They're easy to modify and can sense changes in pH and temperature, making them very versatile. However, hydrogels do have some downsides as well. They can be expensive and non-adherent, might cause dehydration and red eye reactions, and have low mechanical strength and can be difficult to handle and load. Now, provided here is a diagram summarizing the classification of hydrogels. To help us understand and appreciate these classifications more, let's dive into the specifics. I'll break it down for you. Hydrogels can be classified based on their sources. Natural examples include alginate and gelatin, synthetic examples include polyclamide and PEG, and semi-synthetic examples include cellulose derivatives and PLGA, also known as the biodegradable polyester. Hydrogels can be categorized by their polymer structures as well. We have here homopolymer, copolymer, multipolymer, and interpenetrating polymer networks or IPNs. Homopolymer is a polymer that is made from only one type of monomer. Think of it as a string of identical beads. Each bead represents a repeating unit of the same chemical compounds. A copolymer, on the other hand, is made from two different types of monomers. Imagine a string with two kinds of beads alternating or arranged in a specific sequence. This can create materials with a combination of properties from both monomers. When we talk about multipolymers, we're referring to polymers made from three or more different monomers. This variety allows for even more customization in terms of properties and functionalities. It's like having a necklace with three or more different kinds of beads, giving you a very unique and tailored design. IPNs are a bit more complex. They involve two or more polymer networks that are physically intertwined but not covalently bonded to each other. Imagine two nets tangled together, each retaining its own structure but also working together to provide a combination of properties that wouldn't be possible with just one type of polymer. Moving on, depending on their ionic changes, hydrogels can be classified as neutral, anionic, cationic, and ampholytic. This configuration can vary as well: amorphous, semicrystalline, and complex. Finally, the way hydrogels are cross-linked includes free radical processes, chemical methods, enzyme-catalyzed reactions, and psychochemical interactions.
There are different kinds of hydrogels that are used as biomaterials, yet differ in application. These following hydrogels are designed for biomedical applications due to its high water content and biocompatibility. The most widely used polymer is the acrylic-based, known for its versatility, and one most common type of this is FEMA. It is known for its resistance to degradation, stable swelling, and mechanical properties, ideal for contact lenses and drug delivery. Next is the PVA, known for its non-toxic property and favored due to its high mechanical strength and low friction coefficient. This is preferably prepared by the process of freezing and thawing to produce semi-crystalline gels. Similarly, PEG is non-toxic, but this is recently recognized for low protein and platelet absorption, making it suitable for drug delivery systems and biomedical coatings. The degradable hydrogel, as its name suggests, its property is degradable by means of hydrolysis or enzymolysis, which is ideal for drug delivery and scaffolds for tissue engineering. Following to that is the star-shaped polymer that contains numerous amount of functional groups present on its small molecular volume, making it to have a large biological functionality suitable for drug targeting application. And lastly, is the self-assembled hydrogel structure is a new method for preparation of hydrogel that self-assembles into one-dimensional supramolecular structure that is ideal for drug delivery and implantable biosensors. Compared to the previous hydrogels, these stimuli-responsive hydrogels, are known as smart hydrogels, have a capability to change its swelling factor as a response accordingly to environmental stimuli. The pH-sensitive hydrogels have acidic and basic pendant groups that can ionize in response to pH environment, altering the polymer's dimension by swelling or shrinking. Similarly, the pH-responsive do also respond to pH fluctuations, but changes in structure and property, such as conformation, solubility, configuration, and more. The temperature-sensitive are hydrogels where when it reaches below its lower critical solution temperature, polymer becomes soluble and expands. Otherwise, the shell collapse. While affinity hydrogels are sensitive to environmental factors, and as a response, it changes its formation of interpolymer complexes. Moving forward, here are some uses of hydrogel in biomedical industry. The first biomedical application for hydrogel was contact lens, where PHEMA was firstly introduced. It was known as a soft and flexible contact lens that has high oxygen permeability, allowing the oxygen to pass through the cornea. With that, PHEMA becomes the major component and part of intraocular lens. Over time, the contact lens becomes thinner and for treating other eye medical conditions, such as astigmatism, were then produced. Next is the blood contacting hydrogel. This refers to non-ionic hydrogels that interact directly with the blood, as these hydrogels tend to minimize protein adsorption and platelet adhesion, as I mentioned earlier in PEG hydrogel, which is then preferably utilized for this application. Meanwhile, drugs that bind to the target cells are incorporated in hydrogel, as well as once in contact within the body. This is then diffuses the drug into targeted area that was engineered to respond to a specific stimuli, exclusively certain for that area. Hydrogel is also a common biomaterial as scaffolds, as it can maintain its 3D structure. Moreover, it can repair and regrow damaged tissue, showing a great potential in treating tissue injuries. Hydrogels are also ideal as a treatment for skin wounds. Due to its mechanical protection and water content, it keeps the wound warm, moist, and importantly, protected from foreign particles. From that, hydrogels are remarkable with a vast potential for innovation in various fields. As we explore the hydrogels, we understand that it has unique properties, allowing them to be ideal in biomedical application. As we further develop and research this biomaterial, we may find more interesting properties of hydrogel. This may revolutionize healthcare and beyond.